Hi class, today we'll be talking about the law of sines. If you remember in chapter 4, we looked at techniques for solving right triangles. But if we don't have a right triangle, we can't use those techniques. Using the law of sines, if we have an oblique triangle or a triangle that's not a right triangle, then we are able to solve for the missing pieces, whether it's an angle or a side. Basically, if A, B, and C are measures of the angles of a triangle, in lowercase, A, B, and C are the lengths of the sides opposite those angles, then lowercase a over sine of A equals lowercase b over sine of B, and lowercase c over sine of C. Or, same thing, we have sine of A over lowercase a equals sine of B over lowercase b. And that equals sine of C over lowercase c. And again, our lowercase letters are referencing sides of the triangles. And then our uppercase letters are representing that angle. So angle A, and the side across from it is lowercase a. All right. First example, solving a triangle for its missing measurements when B equals 28.7 degrees, C equals 102.3 degrees, and lowercase b equals 27.4 inches. So solving for its missing measurements includes sides and angles. This is what we were given, so we should draw a diagram. We're just going to draw a triangle that's not a right angle. Kind of looks like one, but it's not. And then label everything we have. So see, that's A, B, and C. If angle A is here, the side across from it would be lowercase a. We're not given any information about that. Angle B, we do know, so 28.7 degrees. And the side opposite, we also know, 27.4 inches. Angle C, we know, so 102.3. The side opposite that, we don't know, so lowercase c. You could give A and C different variables. We also are missing that angle A. So I'm just going to solve for that angle A first. I know two angles of the triangle, and if I want to find the third, throwback to how many degrees a triangle's angles or interior angles add up to. So these should all add up to 180. So if I just took 180 minus all those angles, so 102.3 minus 28.7, I would get the measurement of angle A, which is 49 degrees. So I could label that in my diagram. This is obviously not drawn to scale. Now I'm still missing a side A and a side C. So let's use the information we do have to help us find side C. So say we have side C over, using our law of sines, sine of angle C, and then we want to use a side and angle that we do know. So we don't know what this angle or side is, so we're not going to use that one, but wonder about B. We know the side and the angle. So we're going to set that equal to 27.4, that side, over sine of angle B, 28.7. Now we just have one variable that we can solve for. With this law, these are all equal. So I could have set it equal to any of these. It doesn't have to be all of them straight away, but this will help us find that variable. So to get C alone, I'm going to multiply it sine of 102.3 on both sides. I'll have 27.4 times sine of 102.3 all over sine of 28.7. Putting that in our calculator, we want to make sure we are in degree mode. We should get 55.74, let's say 7. 2 decimal places is fine. 3 is a little more accurate. So this is what C equals, or that side C. And we are just missing one last side. So we are going to use this same method. We want to solve for A, or side A, over sine of 49 equals, and now we can use either side and angle because we have every other value. So let's just use B again. 27.4 over sine of 28.7. To solve for A, we're multiplying sine of 49 on both sides. When we put that in our calculator, we should have got 43.061. So we solved for all the missing sides, angles, all the measurements of the triangle we know. Let's do a little application of the law of sines. We have a pole that tilts towards the sun at an 8-degree angle from the vertical. I know I'm going to need to draw a diagram, so let's just kind of sketch what we have so far. Here's maybe our sun. And we have a pole that's tilting towards it at an 8-degree angle from its vertical. So say this would be the vertical. If that pole is tilting towards it, in between here is 8 degrees. So between the ground and that pole, we have 90 degrees plus 8. So this whole thing is 98 degrees. And this is our pole again. Okay, it casts a 22-foot shadow. So let's just use this as our shadow. That is 22 feet. The angle of elevation from the tip of the shadow, right here, to the top of the pole is 43 degrees. So from here to the top of the pole, angle of elevation, so line of sight up, is 43 degrees. And it wants us to find how tall the pole is. So let's give our pole the variable p, and that's what we want to find. All right, so we might have to solve for some missing measurements first in order to help us find what the height of the pole is. We're going to use the law of sines. So if we are trying to solve for p, I could do p, or this side, over sine of 43. So p, or pole, over sine of 43 degrees. And then I want that to equal a side over that angle opposite. So we have this side, but we don't have the angle opposite of it. So we would need to find that, which we could easily do given the other two measurements. We're trying to find that top angle. We have 43, 98, and I know that triangles add up to 180. Just going to do 180 minus 43 minus 98. So that top angle is going to be 39 degrees. So now I can set it equal to that side, 22, over sine of that angle opposite. So sine of 39. To solve for our pole, I need to multiply sine of 43 on both sides. But it cancels out on this side, and my pole equals 22 sine of 43 over sine of 39. When we enter in our calculator, we should have got 23.842 feet, since we're talking about the height of the pole. All right, let's do another application, kind of reviewing our nautical information, our bearings. So we have the course of a boat race starts at point A and proceeds in the direction of 52 degrees southwest to point B, then in the direction of 40 degrees southeast to point C. And finally, back to A. Point C lies 8 kilometers directly south of point of point A, and approximately the total distance of the race. Okay, so some things to review before we draw our diagram is I'm going to draw a little north, east, southwest diagram to help me sketch it. So if it's saying southwest, southwest is in this direction. So if I was starting here, I'd go this way for southwest. Some other things to remember: bearings are always in reference to north-south. So our bearings to north/south. So up and down. So the angle going from there is always the angle going from the north-south line. All right, let's draw a diagram. So the course of a boat race starts at point A. So let's just say our point A up here. It goes 52 degrees southwest. So remember, southwest, we're going this direction to point B. And then in the direction of southeast, 40 degrees. So southeast this way, you want to go in this direction. So down this way to point C. And then finally back to A. So then back up there, which completes our triangle. Okay, let's draw in now our degrees. So in direction of southwest, 52 degrees. So from A to B, 52 degrees. This is our north and south. So this is that angle right there. Then when you're at B, you're going southeast 40 degrees. Remember, it's everything in reference to north-south. So it's going to be this angle down here, 40 degrees. Which we could fill in another angle, since I know this angle is congruent to this angle. This is also 40 degrees. Remember, a line cut by transversal, or transversal cut two lines creates congruent angles. What else did they give us before we can start? solving for some things. They gave us an 8 kilometers directly south of point A. So from here to here, we have an 8. And that looks about it. So approximate the total distance of the race course. So from here to here to here and then back. We might want to label some variables. We don't know from A to B, and that's across some angle C. So let's give that a lowercase c. We don't know from B to C, but that's across from A. So we give it a little A. And then B we do know. So we're good there. We are missing this interior angle right here, but we know 52 and 40, so we could just do 180 minus 52 minus 40. So 180 minus 52 minus 40, we get 88. That's just going to help us with solving for the distance of the sides. So let's solve for side C first. I don't know what side C is, but I know the angle, so sine of 40. So it's using law of sines, so the side over sine of the angle opposite equals, and then now we want to use one that has the angle, has the opposite side. We know those values. This is the only side I do know, so 8 over sine of 88. To solve for C, I multiply sine of 40 on both sides, and I get C equals 5.145. So that's the distance of this side over here. I could even label that on my diagram. 5.145. Now I'm just missing this side length. So side A over sine of 52 equals, I can use either side and angle because now I do have this value. This is a nice clean number, no decimals, so I'm still going to use side B and sine of angle B, so 88. If I solve for A, I'm multiplying sine of 52 on both sides, and I get A equals 6.308, which I could label if I would like, 6.308. And to find the distance of the whole race course, we want to add up all the sides for the course's total length. So I'd have 8 plus 5.145 plus 6.308. 8 plus 5.145 plus 6.308. The whole race would be 19.453 kilometers. That's the whole race. All right, for the U try, I'm going to have you pause the video. Remember to draw a diagram, label what you have. Remember our little reviews of bearings. And then when you're done, unpause and check our answers. So we are given a small lake. A child swims from point A to point B at a bearing of 28 degrees northeast. The child then swims to point C at a bearing 58 degrees northwest. The point C lies 800 meters due north of point A. How many total meters did the child swim? Drawing a diagram. We are starting at point A, going to point B, then point C. So we just want the total they swam. So A to B to C. Let's label what we have. 28 degrees northeast to B. To get to C, a bearing of 58 northwest. Remember, everything's in reference to that north-south. So 58 would go right here. We have congruent angles here and here. So this is also 58. To find this angle, we could just do 180 minus 28 minus 58. There's other ways we can also come about that. This is congruent to this. But we end up with this angle being 94 degrees, whether we subtract these two from 180 or 180 here, etc. Let's label our 800 meters. A to C was a distance of 800 meters. And let's solve for what we're missing. So we're missing sides C and we're missing sides A, and we really need those to see the total distance this child swam. So let's solve for A first. A over sine of the opposite angle, which is 28, equals, we want to use one that we have. So we have the side B, 800, over sine of that opposite angle, 94. Solving for A, we should get 376.494. So that's one side length. And then now let's solve for our other missing side. So C over sine of 58. I'm going to still use my given side because no decimals. So 800 over sine of 94. Small for C, I get 680.095. 3 decimals again is good. 2 is fine. 3 is more accurate. To find the total distance the kids swam from A to C, we just need to add those up. We add 376.494 plus 680.095. We would get 1,056.589. And we are in meters. So that kid swam 1,506.589. On this, we'll stop notes for today, and we'll continue with the law of sines next class.